Okay, so today I'm going to do a little demo to show what collisions look like and in terms of conservation of momentum. And so this is an example from some of your worksheets, and I'll explain what's going on here. So I've got two carts. These carts have equal masses. This cart is the same mass as this cart, okay? And I have them sitting on this frictionless, more or less frictionless track, okay? I have a plunger, a spring on one of these. You can see it right here. And when I press this button, this springs out a plunger and it will push these two apart. So it's sort of akin to an explosion, okay? So there's gonna be a spring between them that's gonna push them apart, or you might think about it in terms of an explosion that's gonna push them apart. So what I want you to watch for is when I hit the button and they go and they move apart, when the spring is activated and they move apart, look at the velocities of the two carts. Okay, one's going to go to the right, one's going to go to the left. Okay, watch the velocity of the carts. So here we go. Okay, now I know that happened really quickly, and now I didn't have anything to really measure that, but if you noticed there, the velocities of the two carts going apart was the same. Okay, now let's explain why that's happening. Okay, these two carts have the same masses. Prior to the explosion going off, the momentum of the total system, the two carts, is equal to 0. Okay, it's equal to 0. They both have mass, but neither one has velocity. Their velocities are both 0. So the total momentum of the two cart system is equal to 0. Well, since momentum is always conserved in any isolated system, right? Momentum is always conserved. After I explode them, okay, after I hit the spring, one will go to the right, which will be a positive momentum. One will go to the left, which will be a negative momentum, okay? So this cart will have positive momentum. This cart will have negative momentum. But if I add those two together, their total momentum of the two cart system will be 0 after they spring apart, okay? So I'll do it one more time just to show you. Okay, here we go. You notice? Same velocity. Same mass, same velocity. One's right, one's left. Total momentum for the two cart system is 0. Okay? Now let's try a little experiment and we'll see if we can enhance this. So I'm going to do exactly the same thing again, except this time I'm going to double the mass of the cart, of one of the carts. I'm going to double the mass of, I think I'll double the mass of this one, okay? By putting this weight on top of it, okay? So now this cart is much more massive than this cart, okay? But again, this has no momentum to start prior to doing this demo, okay? Prior to hitting the spring. When I hit the spring, whatever the momentum is of this cart going to the right, with positive momentum, has to equal the negative momentum of this cart going to the left. So, since this is more massive, what would your hypothesis be about the velocities of these two carts? Okay? What would your hypothesis be about the velocity of these two carts? Let's do it and then watch this carefully and then we'll talk about it. So here we go. Okay? You notice this, I'll do it one more time. Hopefully. There we go. Do it one more time in case you missed it. You notice the velocity of this cart was much larger than the velocity of this cart. Okay? But the momentum of this cart had to equal the momentum of this cart. So the total momentum would remain, so momentum would be conserved and the total momentum would be 0. So since this has much more massive, then the momentum, which is the product of the mass and the velocity of this cart, has to equal this cart. Okay? So the velocity of a more massive cart is going to be slower. When you have an explosion or a spring, the momentum is going to be equal, but this is much more massive. This is going to have a lower velocity. This is going to have a faster velocity. Okay? Okay, now let's try another case. A collision case. Okay, in this case, we're just going to have a cart at rest, and I'm going to push this cart toward it. Okay, think about a hypothesis or what might happen here. Okay, as I push this cart to the right, the total momentum of the system is going to be positive to the right. There is going to be some momentum because this cart's going to be moving. This cart is not. Okay, But watch how the momentum changes when they collide. You notice that the momentum of this cart is transferred almost completely to the momentum of this cart, such that when you do this, the velocity of this cart is essentially the same as the velocity of the cart after the collision. Okay? So all the momentum of this cart is transferred pretty much to that one. Okay? This is an elastic collision. In other words, none of the momentum is always conserved, but none of the kinetic energy is lost either. Okay? The kinetic energy is also conserved. Okay? One last one. Let's flip this to where these join together. So they're attaching to each other. Okay? Okay, so in this case, the cart that's at rest is going to be hit by the moving cart, but they have a magnet and they're going to attach. Watch what happens to the velocity after they attach. Okay, here we go. Fast velocity. Thanks. Much slower velocity. You notice that? So in other words, what's happened now is the mass of the system, the momentum has not changed. What's happened is the mass of the system are these two masses. This is moving, okay, half of the mass. When they attach, now the mass is one single mass, okay? But the velocity is halved, okay? So let's see that again. Interesting, huh? Isn't this interesting? This makes physics so much fun, right? Okay, talk to you later.